For problem solving, let me talk about that. What were the common methods or techniques that one uses to solve? Probably the number one would be using conversion factors, you know, the conversion factor calculation or dimensional analysis. Just making sure the units work out. What else did we encounter? What else we encountered was like algebraic equation. You know, sometimes we're given algebraic equations. Okay, thanks. Algebraic equations would be like degrees Fahrenheit is equal to 9/5 degrees C plus 32 degrees. Another example would be Q is equal to MC delta T. Another example would be M1 V1 is equal to M2 V2. So there are some things we do. Although this one we could do dimensional analysis as well. So I'll put a little asterisk there. That we could have used either one or two for that. Do you guys recognize this equation? What is this one? Is this the stoichiometry for titration equation, or is this solution dilution, or is it both? Some people in Chem 4 use this for titrations, but it's not for titrations. It only works for titrations if it's a 1-to-1 mole ratio and you ignore units. Otherwise, it doesn't properly work. This is for solution dilution. And so normally when we buy solutions, we buy the concentrated stuff and then dilute it down. And so this equation we use. So for example, today we're supposed to make a solution. What's the sodium hydroxide? What are we supposed to do with our sodium hydroxide? Do we do anything with that? So you'll want to skim the lab before coming in to see. Are we diluting it? And what are we diluting? 6 molar. In fact, we buy concentrated sodium. Well, actually, we buy solid. Solid's as concentrated as you can get. And then make a solution. And then if we need something less concentrated, we'll dilute it down. So in this particular case, what we want to do is we want 6 molar and we want to dilute it down to about 0.1 molar. However, we want to actually, I don't know how precise we have to be for this, because when the stockroom dilutes it down to 6 molar, is that 6.0 molar, 6.00? We don't know what the precision of this dilution was. And so we'll just take it as this. What we're going to do is we're just going to do a rough dilution. And so if I want to take 6 molar and dilute it down to 0.1 molar, the first thing I'm going to ask is how much do I need? Should I use all the 6 molar I got, or do I have to use it all? And so about how much of the 0.1 molar are you trying to make? 500 milliliters. And so we need about 500 milliliters. So this is not very precise. This is what we call our stock solution. Sometimes our stock solution is very precise, but this particular stock solution is not very precise. And this is going to be a rough dilution. A rough meaning like a qualitative. Dilution. And so what we do is we just use the solution-dilution equation. And so this I'll call M1, you know, the initial concentration. This is M2, the final concentration. And this is V2, the final volume. And so we're going to solve for V1. V1 is our unknown. So how much of the concentrated stuff are we going to need? So V1 is equal to M2 V2 over M1. Sorry, M1. And so we'll just write M2 over M1. I'm going to write this in parentheses, although parentheses are not necessary here. But I'm going to write this in parentheses because I want to highlight this. This is called the dilution factor. When we do solution dilutions. And so M2 is 0.1, M1 is 6, and we want 500 milliliters. And the molarity cancels. And so how many milliliters is this? Give me one more digit. Now we're only allowed 1 sig fig here, and so it's about 8 milliliters, but we want to be a little bit more precise in our measurement because we want it close. We're going to assume that the stockroom made it right on 6 molar, but they probably didn't. It's anywhere around 6 molar. But we'd like to use 8.33 milliliters. Now we're going to measure this out using a 10 milliliter grad cylinder. You don't have to be super precise. Let's say we accidentally overshot a little bit. If we accidentally overshoot it, are you going to worry about it much? No, don't worry about it. You know, just try to get it close to 8.33, but don't spend much time getting it exactly. So you aren't going to get a dropper and drop it in there. And the reason you aren't going to get a dropper and drop it in there is because of this. This stock solution is only good to 1 or 2 sig figs, you know, and so we don't want to overdo it. So what we're going to need is 8.33 milliliters of 6 molar sodium hydroxide. And then what we're going to do is we're going to pour that into a 500 milliliter Florence flask. But the Florence flask is not calibrated. And so what they do with these is they design them to hold more than 500 milliliters. So we're just going to guess where 500 milliliters is. So when we pour this is just 8.33 milliliters. And then we're going to add water. So the Florence flask is this round one. This is not volumetric glassware. This is volumetric glassware here. This is a 250 milliliter volumetric flask. And this one has an etch mark in here. You can feel it with your fingernail. This etching here comes where they pour in 250.00. Even though this says 250, this is good to 5 sig figs. It's 250.00. And if you fill it to this mark with the meniscus right on the mark there, it's 250.00 milliliters. So this is a volumetric flask. This is not. And so we're just going to guess how much water we're going to put in. And we're going to add water up to the neck. And then we're going to say, does it say up to the neck? Yeah, and so we're going to say that's approximately 500 milliliters. So that's good. If I were to err on this, I'd err on the high side. You know, you don't want to go low on this. The reason you don't want to go low is because we don't want to risk having to titrate with more than 50 milliliters. If you have to titrate with more than 50 milliliters, that means you have to refill the burette, and you don't want to have to refill the burette in the middle of a titration. It just means more work for you. So I wouldn't worry about overshooting this a little, especially if this was undershot. If this were undershot and you undershot this, then it could be quite a bit more dilute than what you expect. But we don't want to make it too concentrated either, because if we make it too concentrated, then we don't add a large enough volume of titrant. When we have a burette like this, what's the optimum volume of titrant that we'd like to use? For sure, we want to use more than 10. If we use more than 10 milliliters, then that gives us 4 sig figs, because it's going to be at least 10.xx milliliters. And so, but the relative error, like let's say we make a 1 drop error in 10 milliliters versus a 1 drop error in 30 milliliters. A 1 drop error in 30 milliliters is a much smaller relative error. And so we like to use a larger volume. Therefore, if we overshoot it by a drop or undershoot it by a drop or something like that, it's less significant than a smaller volume. And so we'd like to use a volume around 30 to 50 milliliters. And so like 40 milliliters is good. Using that kind of volume, well, it depends on the concentrations, so we'll see. So what we have here is this should be about what molarity? About 0.1 molar. And then we're going to do a process. This is experiment or part, what do they call it, part 1 or part A? They call it part 1. And what's the title of part 1? Standardization of a sodium hydroxide solution. And somebody remind me what standardization means. Standardization is one of the big processes that we do in the laboratory. You know, standardization or using. Have you ever heard of the? They used to call it NIST, NIST. NIST stands for National Institute of Standards and Technology. And so they're all into standards and standardization. They have the budget of over $1 billion a year. So what is standards and standardization all about? Ashley? Yeah, we want to know how much is in there, and to the highest precision and accuracy possible. Maybe not, I don't think we'll get it to the part per million or part per billion, but something, you know, decent would be good. The more sig figs, the better. And so typically we think in terms of sig figs. We get it to about 4 or 5 sig figs is good. 3 sig figs would be like the part per 100 level, you know, kind of. 4 sig figs part per 1,000 level. 5 sig figs a part per 10,000 level, you know. Part per billion or part per million is going to be tough, probably. But doable, probably. So we're going to standardize the sodium hydroxide by titration against the primary standard. a primary standard has to meet certain criteria. Number one, you have to be able to purchase it in high purity, and so available in high purity. Number two, it has to be stable enough that you can weigh it. And so it needs a stable, weighable form. This sodium hydroxide is not what we'd call a primary standard, but we're going to standardize it. And standardizing is just figuring out what its concentration is here to as accurate and precise, as accurately and as precisely as we can. But primary standards are different. When we're doing things like measuring volume, that's not so easy. Like the burette, how many sig figs am I going to get from the burette? 4 sig figs. As long as I go over how many milliliters? 10. So for example, if I'm at 8 milliliters, it's only going to give me 3 sig figs, 8.xx. But our balances, how many sig figs can we get from those balances? Yeah, it depends on how heavy it is, you know. Let's say if something weighed 10 grams. If something's on 10 grams, then how many sig figs would I get from that balance? It goes to the 4th decimal place, so that would give me 6 sig figs if something weighed over 10 grams. If something only weighed in single digits, then that would give me 5 sig figs. So I'm looking at, if it weighed less than 1, it'd give me 4 or something like that. So I can get a lot of sig figs. And so primary standards have to be weighable. Because when we weigh things, we can weigh things much more accurately than measuring volume. And what's our primary standard that we're going to use today called? These are all things that would be on like a pre-lab quiz. Yeah, oxalic acid dihydrate. Yeah. And so the one we're going to use today is oxalic acid dihydrate. This is a stable hydrate. What it means to be a stable hydrate is that it stops at the dihydrate, and so it's not easy to lose. Once those two waters get incorporated, oxalic acid has these molecules, and they pack together to form a lattice, a molecular lattice, and these water molecules can wiggle their way into the lattice, basically. And the dihydrate is stable. That is, it doesn't easily lose the water and doesn't easily gain more water. In fact, this is a stable hydrate. And so this is what we're going to use. Now, the anhydrous form of oxalic acid is not stable. So let's say we cook this stuff at like about 100 degrees, 100 plus degrees C. And what's going to happen is if we warm this stuff up, it's going to drive off the water. If it drives off the water, then what we have is dry anhydrous oxalic acid, but we live in a humid environment. If the relative humidity here were 0%, then the anhydrous form would be the stable form. But the humidity here is like what, 30% or something like that? And so that means everything's going to rehydrate. You know, if you go out in the desert, maybe it's okay. If we lived out, well, it depends on if they have a humidifier on or not, but if we're out in the middle of the desert, then we probably want the anhydrous form, not the hydrated form, because the hydrated form will dehydrate. Well, anyway, so we're going to do this, and should we measure its volume, or should we measure its mass? Its mass. Its mass is a heck of a lot easier to measure out than the volume. And so what we're going to do is this. We're going to make an oxalic acid standard solution using the primary standard oxalic acid dihydrate. Okay, so how many sig figs does this 250 milliliter flask give me? This is a volumetric flask. 5 sig figs. This is 250.00. And the balance I'm going to get, well, it depends on how many grams. About how many grams of oxalic acid dihydrate do I need to weigh? 2.5. Did you do the stoichiometry calculation? Oh, good. That was a pre-lab question. Right. Anybody else do it? So about 2.5. I would say if you're going to err, maybe err on the lower side. Don't go big here. Let's say you go 3, you're going to be using a lot more sodium hydroxide. You might run out. Because what would happen if you go below the 50? If you go below the 50, you've run out of markings. Do you know how much you've added? No, what would happen is you throw that experiment out. You just blew it by going over 50. You can't go over 50 on this because there's no way to measure it. That's like the Moore pipette. When you're using the Moore pipette, rather than having a stopcock to control this, we have our thumb. And you're going from 0 to 10. If you go below 10 in a Moore pipette, that is, if you don't stop it before it hits the 10 mark or at the 10 mark, then you just blew that run. Basically, you have to toss it out. But this is a lot easier to control because we have a stopcock here. Do you have to start at 0? No, we don't have to start at 0. In fact, some people consider it poor technique because it makes you slow. If you have to start at 0, then you're there with a dropper or a spray bottle, and you're wasting time getting it right on the 0 mark. And so if some people see you do that, they're going to think, oh, you're probably slow in lab. You're not a fast person in lab. That's one of the assumptions a more skilled person might think. It's fine that if you want to start at 0, it's fine. But you don't have to start at 0 because whether you start at 0 or below, you still got to read it anyway. So why not just start below 0 and just read where it is? It's not going to take. The other reason you might start at 0 is because you don't know how much it's going to take. You might start at 0 to give you the maximum volume because we don't want to go below 50, because if we go below 50, then we have to refill it. Actually, before we get to 50, we'll have to measure it and then refill it and then measure it again and then start adding more. Right? And so the other reason is, if you start at 0, that might actually be good technique because you're trying to maximize the volume that you have here for your titration so that you don't run out. But let me tell you, somebody already did all the calculations for you. And so if we use the amounts, you're not going to go over 50 per titration. We should be in the optimum range of 30 to 50 milliliters. Actually 30 to 45. If we're getting close to 50, it's getting too risky. And anyway, so there's a pre-lab calculation. You have to calculate about 2.5 grams. I'd go less than 2.5 grams. Now, the problem is, and I saw that some people spilled some of their solid outside. If you spill some solid outside the balance or on top of the balance, get a damp cloth, not cloth, but damp paper towel and just wipe it up. That should be all right. Yeah. Although damp, it might create some corrosion with the salt water. So we have brushes too. You don't want to inhale any of it though. Oxalic acid as well. Oxalic acid, this is poisonous. Give me the formula for oxalic acid. dot 2H2O. This is a solid. So we weigh about 2.5 grams, and I recommend that you use a beaker. I don't recommend you trying to put it in this. And you could open the top window and tear this and zero it, right, and then add it directly to this. But we don't have a funnel here. If we had a funnel, it might be easier. Actually, so there you have two options here. Option one, we weigh it into a transfer beaker like this, and so we tear the beaker and then add it to this, and then we transfer it over here into our flask, and then just wash it in with a spray bottle, any residual crystals stuck on here. That's option one. Option two, let me show you the second option in weighing this out. This is the low budget weighing paper. You can buy actual weighing paper. We have weighing paper, weighing boats. There are all kinds of stuff that, if you have the budget, you can use. This is low budget method. The low budget method is just to get a piece of paper like this and then fold it in half, and then fold it in half the same way. So you make a little dish like this, and then tear this, then tap on your approximately 2.5 grams of oxalic acid dihydrate, and then we could use this to transfer it directly over here. Okay. This way the crystals don't get stuck on the glass. The crystals like glass too. Sometimes, especially if they're wet a little bit, they like to stick. But dry paper should be good. Just be careful not to spill any on the outside. You could use the funnel that you have in the drawer too. That's another option. It's just, if you use the funnel, that's probably safer, and then wash it in. Do it that way. But it also means more cleaning, other things. Normally I just try to tear the vessel I'm weighing it in, but the mouth on this is too small. All right, so what we're going to do is we're going to weigh this to, if it's 2.5 grams, so it's going to be 2, we need to weigh it to 2.xxxx grams. That's 5 sig figs. And then we're going to transfer all of this into a 250 milliliter volumetric flask. This is not a good drawing. And there's going to be etch mark on here somewhere. So we transfer it all in there, and then we add water. To the mark. But we don't want to add water to the mark. You think, okay, I better add water to the mark. No. What we'll do is we'll add maybe 2/3 full like this. And then mix. If we add it to the mark, it's so hard to mix. Now mixing this, there are a couple of techniques that we could use to mix it. So let me just get some water in here. One technique is just swirling it. Because you got to get the oxalic, even though oxalic acid is pretty soluble, it still takes some work to get it to dissolve. And so if you fill this to the mark here on the neck, it's so difficult to swirl. It takes you so long. All right, the other technique, I don't know if you want to do this, depends. Is the stopper clean? We have two types of stoppers for this. If you look, this is called a ground glass joint here. And we have a ground glass stopper that fits perfectly on that. We might not have it anymore. And so that's probably why there's a rubber stopper on here. If the rubber stopper is clean, or if you have the ground glass one, you put it on there, give it a little twist, or we have plastic ones. The plastic ones have a little play on the handle. So if you twist it left, it contracts. If you twist it right, it expands to lock in to place. It depends on what. We have 3 types of stoppers you might get. Straight ground glass stopper, rubber stopper, or plastic stopper that expands and contracts. Okay, if you got the stopper on there pretty good, then what a lot of people like to do is they like to do this inversion, because this mixes things quite rapidly as well. And so they'll invert it a bunch of times, and then it's good. Okay, once it's well mixed, then we're going to fill it to the mark. Here. Okay. Let me try to fix my drawing. What happens if you overshoot the mark? You only have one chance. This happens every semester. Somebody overshoots the mark. What happens if you overshoot the mark? You gotta start over. You dump it, wash it out with DI water, and start over. You don't have to dry it. This thing would be very difficult to dry. Yeah. Technically, no. I mean, that would be better than nothing. But, you know, assuming that it depends on how well mixed it is. If it's well mixed, then it rapidly diffuses. And so if you use a medicine dropper, you're not just getting water, but you're also getting some oxalic acid molecules. And if you're doing high precision work, you can't do that. Yeah, you got to start over. How much does it suck to start over again? A lot. You know, how much time does it take? A lot. And so you have to be very careful at this step. Don't overshoot. You could fill it with a spray bottle up to about here and then go to medicine dropper. People who use the spray bottle accidentally spray too much. Some people have pretty good control. But I just wouldn't risk it because the consequences of overshooting are too big. So don't overshoot the mark here. Make sure you get that right on the meniscus. I mean, right on the etch line here. Hopefully it works out well. Turn this on. Now what we just made is something called, do you know what we just made? Oh, no wonder. Out of memory. This is called standard oxalic acid solution. It's a standard solution. What qualifies it as a standard solution? Well, one thing is we'll know the concentration. The concentration is, in terms of molarity, is going to be, we're going to do another calculation here. We're going to take our 2.xxxx grams of oxalic acid, which I'm going to abbreviate oxac, dihydrate. Maybe 2H2O is the easiest to abbreviate it that way. And then I'm going to convert it to moles. So when I do this, there are some things that I like to memorize. I have these molar masses memorized. Hydrogen, what's the molar mass of hydrogen? 1.008 or 1.01 in compounds. In elemental form, either as atoms or H2, I use 1.008. I use 101 in compounds. Carbon. I use 12.01. I don't go 1-1. It's just, this is all for speed. You remember I told you I was training for speed? I do this so I can calculate molar masses quickly. Oxygen, 16.00. I don't use 15.994. It's too slow. And so let's do this. How many hydrogens do I have? I have 2 plus 4, 6 hydrogens. Do you see that? So what's the mass? 606. How many carbons do I have? 2 carbons, that's 2402. How many oxygens do I have? I have 6 oxygens. So 2 oxygens is 32. So 32 plus 32 is 64, plus 32 is 96. And so that would be 9600. And then I'll just add this up. And so oxalic acid dihydrate's molar mass is going to be 8, 0, 10, 16, 126, 08. Is that what you guys got? That's what you got? Good. Okay. You have to include the waters because the waters are going to affect the mass. And so we need the mass of that. And so it's 126.08 grams per mole of oxalic acid dihydrate. I'm going to call it OAD because I'm running out of room. OAD. And then when you dissolve this in water, what happens is the molecules get pulled apart. When the molecules get pulled apart, the waters that were originally trapped in the maze of passages or what we call void spaces or interstitial sites, the waters get freed. You know, when you break apart the jail that holds the water molecules in there, the waters are free. And then what we end up with is a mole ratio. 1 mole of oxalic acid per 1 mole of oxalic acid dihydrate. And so this gives me moles of oxalic acid pure. And then I know what's the volume. If I hit it right on the mark, what's the volume of that volumetric flask? 250.00 milliliters. And then I'll convert that to liters. 1 liter is 1,000 milliliters. And this gives me moles per liter. And so what I know this, I'm going to know the concentration of my oxalic acid standard to 5 sig figs. So that's why we call it a standard solution. This is known to 5 sig figs. It's not a primary standard, but you know, primary standard solutions aren't primary standards because you can't weigh. Well, you can weigh them, but it's not as easy to deal with accurately. All right, so what we know is we know the concentration of the oxalic acid. This is just let's pretend this is my oxalic acid. Let's pretend I filled this right on the mark. And so I have my oxalic acid standard solution. And then what I'm going to do is I'm going to pour my sodium hydroxide, qualitative, concentration, into my burette. Usually in Chem, blue usually represents bases, blue for bases, red for acids. But not always, Depends on who used it last. So let's pretend this is my sodium hydroxide solution. I don't want to work with any chemicals right now. Be careful with this burette, because if I break this, you know how much these are? $216, I think, 20 something. I forgot. 2017. I got to look at the price list. Probably now, 400. I don't know. I think everything seemed to have doubled in price. Try not to break this. Oh, should you clean this? I mean, usually blue represents bases, but who knows who used it last and what they put in here. And so probably before I pour in my sodium hydroxide, I probably want to clean this. Now, if it's really dirty, the way you can tell if it's really dirty is you'll see droplets of water adhering to the sides. Well, you don't want to see droplets of water adhering to the sides. That's called beading. What you want is like no droplets. Like here it's clean. Up here it's kind of dirty. There are droplets. You want wetting of the surface. And then you know the glass is clean. Water loves glass, so it shouldn't bead like this. It shouldn't try to stay away from the surface. It should just try to get on the surface. If it's excessively dirty, we should clean it with soap and water, but we're not going to clean it with soap and water. It's going to take too much time. So what we're going to do is we're just going to rinse this thoroughly with DI water. So when we rinse this thoroughly with DI water, we're going to rinse out the stopcock here with DI water, and then we're going to rinse the inside surface of this, like this, with DI water. Dump that. Okay, so you rinse it out a few times, and then we're ready to fill this. But when I fill this, what we do is this. Did I get rid of all the rinse water out of here? No, I didn't. There's still rinse water in here. And if there's rinse water in here, that rinse water is going to contaminate my solutions. Correct? And so there are things that people do. One thing that people do is they dry this out. But how can you dry this out? One way that we dry glassware is we throw it in the drying oven. And so the drying oven's used to dry glassware, but we never dry volumetric glassware in an oven. The reason we don't dry these in an oven is because the glass can soften and change volume. Then it's always reading wrong. That would be an example of a systematic error where the instrument's no longer calibrated properly. And so we are not going to dry this with paper towel. We're not going to dry this in a drying oven. Another technique that people use to dry is to use like ethanol or acetone to wash the water away. If you have some ethanol, you can wash the water out, and then the ethanol evaporates pretty rapidly. But that's expensive, and we used to use acetone a lot. They don't want acetone in the drain anymore. So ethanol is okay, but ethanol is way too expensive. And so how are we going to get rid of the rinse water that is stuck on the surface of the glass? We're not going to rinse with ethanol. We're not going to rinse with acetone. Do you know what we're going to rinse with? We're going to rinse with a sodium hydroxide solution. So in that 500 milliliter Florence flask, you're going to sacrifice some of your I'm just going to use tap water to save money. Stockroom will probably like. By the end of this is fall. By the end of spring, if we run out of money, you're not going to be getting the DI from here. You're going to be getting it out of buckets over there, because that means we've run out of money and we can't replenish the DI. So we have some backup things. Here, you probably should use a funnel. You don't want to spill this on the outside. We have these tiny funnels here that are for the burette, but my equipment drawer is missing a lot of stuff. Or you could use a beaker. A beaker has a spout. It's easy to pour. Do you want to use that much for the rinse? No. We use like 5 to 10 milliliters for the rinse, because what we're going to do is we're going to rinse off the rinse water on the inside and through the stopcock and the tip of this. But since this is sodium hydroxide, we probably want to pour this into our waste beaker. Maybe better. But it's sodium hydroxide of 0.1 molar. I mean, people pour solid sodium hydroxide down the sink, you know, which is drain cleaner, lye. And so do you want to get drain cleaner in your eyes? No, so don't rub your eyes. If your hands feel slippery, don't rub your eyes. It's very painful if you get sodium hydroxide in your eyes. It can cause permanent eye damage. And also, you should wear safety goggles when dealing with sodium hydroxide because of that. All right, so we're going to rinse this with what we call portions. The portions, we have a fancy name for portions of sodium hydroxide solution. Do you know what that fancy name is? Aliquots. We rinse it with several aliquots of, I don't know the origin of that, but rinse it with several aliquots of sodium hydroxide. We're going to sacrifice it and waste it. Okay, once this is clean, now this is wet with sodium hydroxide solution, so we're good. And so I'm going to just go ahead and pour it. There's my imaginary funnel still there. I'm just going to fill the burette. And I'm going to fill the burette above the zero. Why? Do I fill the burette above the zero?
So you can have it on zero. It's up to zero.
I don't want to overfill it where it spills over, but I want to fill it above the zero because there's, do you see that huge air bubble there? There's a huge air bubble. It's about this big. Air is very compressible. If there's an air pocket in here, your volume, you're never going to get very precise results because the air can squeeze down or expand slightly depending on the pressure. And so what we need to do is we need to get rid of this air bubble. But sometimes the air pockets are very stubborn. Sometimes there's air trapped in the stopcock. If you're having a hard time getting rid of the air bubble, then this is what I recommend you do. And that is, when we're trying to purge the air out of here, this is like trying to push a balloon or a ball. Have you ever tried to push a basketball in a swimming pool as deep as it can go? Is it easy to do? No, this is very hard to do. And so this is what's hard to do. You're trying to push this little ball down to the bottom of the swimming pool. It's not so easy. And so what I like to do to get rid of the air pocket is to hold it like, I mean, this is full, but look how much I can tilt this without it spilling out. That's how much water loves glass. Do you see that? The water loves glass and itself. And so what I do is I just hold it like horizontally, and then pushing the ball to horizontally in the swimming pool is easy, right, on the surface. And then you can get rid of it. There's some air pockets still trapped there. Sometimes you'll shake those out. There, the last couple of bubbles came out. Did you see that? And so this works pretty effectively. And now I'm below the zero. I'm not going to refill this. I'm just going to go ahead and read. If you forgot how to read this, let me know. I'll show you how to read it again. But we need to read it to the nearest hundredth of a milliliter. 2 decimal places. Some people read the burette only 1/10 of a milliliter. That's wrong. And so make sure you correct it. Okay, so our sodium hydroxide, I have my initial reading here, no air pocket. Now I'm ready to titrate. We titrate using an Erlenmeyer flask. And it's probably better to use a 125 Erlenmeyer. This is this is a 125. This is kind of small, isn't it? We probably want to titrate it using a 250. And so we're going to have phenolphthalein. The phenolphthalein is going to be located probably in that hood over there. How many drops of phenolphthalein? 2? Okay. Don't go more than 2. Phenolphthalein itself is an acid. So we'll just use a little bit of phenolphthalein. And then how many milliliters of oxalic acid, standard solution, are we going to put in here? 25. 25.0 or 25.00? 0.00. We're going to get 4 sig figs. And therefore we need to use a volumetric. You guys remember using this? So here's where it's going to count. Now the thing is, we need to make sure this is clean. And so what I do is I get a spray bottle and just rinse it with a spray bottle on the inside. Drain it like this. Okay, but now it's contaminated with DI water. And so what do I need to do? Well, I need to give it a final rinse with not sodium oxalic acid standard solution. Am I going to put the pipette? I see this all the time. People put the pipette in here. What's going to happen if I put the pipette in here and it's contaminated with DI water? Yeah, it's going to contaminate. So all that effort in getting it right on the line was just wasted. And so what I'm going to do is I'm going to sacrifice this. And so I'll get a beaker here. This is going to be my sacrifice solution for rinsing. So this is just for rinsing. Okay, if I contaminate this a little bit, no big deal. And so what I'll do is I'm going to rinse this out with some. Remember, if you hold the tip on the bottom, it goes slow. If you raise it a little bit, it'll go faster. Try not to suck in air bubbles in here. And so I'm going to just rinse this out, the inside walls of this, with my primary oxalic acid, and then just dump it into my waste beaker. Do that like 2 or 3 times. It should be clean. Okay, now once I do that, then it's probably okay to do it here. But in case there's an accident or something, or in case to avoid cross-contamination, we like to put it into a transfer beaker. Wow, all the beakers missing. So I would do this. Rather than getting it straight out of here, I get a transfer beaker like this, and then use the transfer beaker to bring it over. Also, although you could do it like this, save time. Once this is cleaned, the outside is cleaned. I'll leave it up to you. But the volumetric flasks are expensive and these pipettes are expensive, so transfer beaker might be less risky. Okay, then we're going to transfer that in here. The way I do transfer it in is just let it drain. And then there's going to be 2 drops stuck or 1 drop stuck in there. What should I do with that 1 drop that's stuck in there? Leave it or blow it in? Leave it. All right, now I'm ready for titration. I know how much acid I have in here, but that's 25 milliliters. Then it tells me to add water. Is it okay to add water? Isn't that going to screw up the concentration? Yes, it's going to screw up the concentration, but we don't care anymore because we know how many moles of oxalic acid we have in here now. Because what we're going to do is we're going to go from 25 milliliters to 0.025 liters, and then we know the concentration to 5 sig figs, and then we can get the moles to 5 sig figs. So we know how many moles of oxalic acid are in this to 5 sig figs. Adding water, is that going to change the number of moles of acid? No, it's not. And so we could add a little bit of water in here. That'll make the titration go easier, and then start titrating. What I do is, oftentimes I'll do a throwaway titration as my first titration. Throwaway titration, that way I know about how much it's going to take. And the throwaway titration is, in Chem 4, you could back up. No titrations were throwaway, because if you overshot the endpoint, we had another burette over here. The other burette was the red burette, which contained acid. We don't have that here. If you overshoot it here, you know what you have to do? Yeah, you toss it and start over. And so, but normally I don't want to take too much time. So I'll wait. I don't even swirl this. I just wait until I get a big burst of pink, and then I'll stop, and then I'll swirl it. okay, it's going to disappear. And then as the color starts to persist more and more, I don't swirl as you go, but some people swirl as they go either. I just go ahead and add. Okay. Now once I get better at this, then I'm going to slow down. So I'm going to go to a drop by drop addition. So we can go to drop there, drop, drop, drop. I can go to a drop addition. And then when I get very close, I'm going to go to half a drop. Can you titrate to within a half a drop? Have you ever done that? A half a drop won't fall. A half a drop stays suspended. So if you look at my burette, I have a half a drop suspended there. Can you see that? There are two ways to get a half a drop in there. One is to tap the tip against the inside wall, and then that half drop disappeared. Do you see it disappeared? That's one way. The other way is get a spray bottle and wash the half a drop in. And then what we want to see is we want to go from colorless to very faint pink within half a drop. And that faint pink has to persist for how long?
15 seconds.
15 seconds? Or 30 seconds? Yeah, 30 seconds. It has to persist for 30 seconds. If it disappears after, if it disappears after 30 seconds, then you're not there. Unless you're breathing on it. If you're breathing on it, then 15 seconds is probably okay, because each time you exhale, what are you exhaling? CO2. And is CO2 an acid or a base? It's CO2 is an acid. So if you exhale on this, the color is going to disappear faster. The reason it only has to persist for 30 seconds is because there's CO2 in this room, and the CO2 is going to neutralize some of the base, and then what that does is raises the pH and it turns pink again. So that's okay. If you get a straw and start blowing bubbles in this, then it'll last like 1 second. You know? Yeah. All right, are there any questions on this titration? So what we want to do is we want to get 3 runs that are close. You know, if we're using 25 milliliters here, then the amount of sodium hydroxide we get should be the same. And so what I like to do is I like to check my precision using the volume. For part 2 we can't. For part 1 we can. And so if you take the you take V final minus V initial, that's the volume for titration 1. Then you do titration 2, V final minus V initial, titration 3, V final minus V initial, and that gives you the volume of sodium hydroxide. The volume of sodium hydroxide should be the exact same in all 3 trials. But do you think they're going to be exactly the same in all 3 trials? No, because what kind of error? Systematic or random error? Random error, most likely. They aren't going to be the same. Systematic error, you can get all 3 the same, but they're off because you're doing something wrong each time, the same way. Well, anyway, so what we're going to do is, as a check, you know, how wide is your spread? You know, between the smallest volume that you used and the biggest volume that you used. And so what we do is we like to get this kind of precision. How much precision do we need? Below what percentage? 0.5? The precision should be less than 0.5% difference. This is in volume of sodium hydroxide. This is for part 1 only. And so the percent difference is equal to the biggest volume minus the smallest volume divided by the smallest volume times 100%. if you're not getting within 0.5%, then do trial number 4. If you do trial number 4, eliminate the one that's furthest, either the smallest or the biggest. Eliminate one so that the 3 are as close to one another as possible. If you do that and you're still not getting within 0.5%, then do trial 5. Then eliminate the outlying one. You know. If you're still not getting it with 5 titrations, then maybe stop there, because you're going to run out of sodium hydroxide. We have to use this sodium hydroxide. We made 500 milliliters, not just for part 1, but this 500 milliliters has to last for part 1 and part 2. So if you're going to start trial 5, then maybe rethink it, come back to it later, because you need to save enough sodium hydroxide so you can do part 2. We're just doing part 1, and then we're going to seal our flask. There are 2 ways we're going to seal this. One is either with a rubber stopper, and the rubber stoppers these all have different sized necks. So we have a whole bunch of different sized stoppers. You got to find the right one. The right one is only going to sink like about halfway or less, like this. If it sinks more than half, there's a risk of getting it stuck in there. If you get a stopper stuck in there, it's so hard to retrieve. So don't get stoppers stuck in the neck. And obviously you don't want a stopper to fall into the solution. It'll contaminate it. Okay, this is too big to fit in your drawer. So what we're going to do is we're going to put it in the cabinet, either against the wall or against this wall over here. There's a bigger cabinet there that we can store it for next time. Okay, the other thing we're going to do today is we're going to weigh our samples. And so that means removing the samples and then cooling them in a desiccator and then drying them. I mean, they're already dried, excuse me. Cooling them in the desiccator and then weighing them over there in the balance room. Once they're weighed, then you can touch with your fingers. You don't have to clean them. You just return it. Return it dirty, that is with the precipitate in there, in the original beaker that's numbered, and the ribbed watch glass, all together to the stock room after you weigh them. So all we need to do is cool desiccator, weigh the cooled crucibles, and handle those with paper towel or tissue until they're weighed. And weigh them dry, okay? All right, are there any questions? Okay, there's one more problem-solving technique here that let me just mention, I'll talk about maybe tomorrow. And that is multiple equations, multiple unknowns. Let me give you a quick example here. Chapter 1, X degrees Fahrenheit is equal to X degrees Celsius. When are these equal? Do you know when they're numerically equal? In other words, we might say this. We might say that X degree or Y, it doesn't matter what I label it, X degrees Fahrenheit is equal to Y degrees Celsius, where X equals Y. This would be a system of equations here. What would be an example of Chapter 1, system of equations? An example of Chapter 2, system of equations would be, you have a mixture of, let's say, sodium chloride and magnesium chloride. And let's say the mixture had XX.XX% chloride. And that is, the unknown would be, we're going to have this. We want to know Y percent sodium chloride and Z percent magnesium chloride. This is chapter 2. In chapter 3, we see this problem-solving method in a couple of problems. One was the combustion of methane and ethane. Methane and ethane, or I don't know, or what was it, methanol and ethanol? Maybe that was it. One of these. And then there's another problem where it was aluminum and magnesium alloy, I think. Aluminum and magnesium alloy. And HCl. This one yielded a unique amount of CO2. This one yields a unique amount of hydrogen gas. So I have a different way. Rather than doing system of equations, I have a different way of solving these that I'll share with you tomorrow. But today we'll just concentrate on the titrations and then weighing, you know. Okay, any questions? All right, I'll stop here and then let you guys get started.